Hi, everybody. We are Team Wing, and our fluid machine was a coffee maker. We'll be analyzing the components of a coffee maker in the order that a fluid particle would encounter each part. We'll start with the reservoir, then the pipe to the check valve, then the check valve itself, then the resistive heating element, then the diffuser, and finally the coffee cup.
So in a coffee maker, the first component that the fluid enters is the reservoir. Now in the reservoir, we can model the pressure distribution of the fluid as a hydrostatic pressure distribution. Per the hydrostatic equation, the pressure within a motionless fluid varies linearly with the water depth. Pressure is largest at the bottom of the reservoir where the one-way valve is located. Here, the force due to the pressure opens the valve. The one-way nature of the valve prevents backflow from other elements. That way, water can only flow down the pipe and not back up. Now, because the pressure difference between the top and the bottom of the reservoir is on the order of about 1,000 pascals, the valve needs to be carefully designed such that it remains closed for normal atmospheric pressure, but opens when fluid fills the reservoir, and causing the pressure at the bottom to increase. For the coffee maker that we dissected in lab, we estimated our reservoir to be about 19 centimeters deep. This means that when we apply the hydrostatic equation, we find that the pressure near the top of the reservoir is about atmospheric, while the pressure near the bottom of the reservoir is a little bit higher than atmospheric at about 103 kilopascals.
The water then flows out of the reservoir down through a pipe. So the pressure from the reservoir causes the fluid to flow down, and in this pipe, the fluid experiences pressure losses proportional to the length of the pipe and inversely proportional to the diameter. This pipe has low surface roughness, and it also has a small Reynolds number because the velocity and the diameter are small. This corresponds to a low viscous dissipation factor on the Moody chart and an overall low pressure loss.
In the middle of the pipe, there's a check valve. The check valve is present to prevent the water from returning to the reservoir after it has passed the valve. If water tries to go back against the direction it's supposed to be going, this forces a valve shut. The shut valve creates an area of higher pressure, which then, through the hydrostatic equation, allows the water to rise above the initial height of the reservoir on the other side of the U that the pipe forms, allowing the water to reach the coffee.
After the water flows through the check valve, it encounters the resistive heat-in the pipe. So when the coffee maker is turned on, the heat-in element is activated, and this heats up the water in the pipe, causing the pressure to rise. And as previously mentioned, the check valve prevents the water from going back into the reservoir, which forces the fluid up into the coffee grounds. And any water that boils due to the heat rises up into the coffee grounds by Archimedes' principle, and this is what causes the gurgling sound that you hear often when you brew coffee.
Here are photos of the resistive heating element on our coffee machine. On the left, you can see it removed entirely from the machine with the circuit exposed. The wire runs through a small metal housing that touches the tube with the water. Resistors lower the voltage to a safe level, and the generated heat from the wire warms the water. There is a small included thermostat for temperature regulation too. On the right, you can see how this element connects to the rest of the machine, and it's through a rubber tube.
Lastly, the heated water runs through the tube and goes through a diffuser. As the heated water moves from the tube into the diffuser to pour over the ground coffee, the diffuser acts as kind of like a free jet issuing from an orifice. Here on the left, you can see the diffuser that the water dispenses out of, and by the Torricelli relation, the velocity is proportional to the pressure of the water, and proportional to the pressure of the water. And because of the higher pressure due to the heated water, it will issue downwards and will go through the coffee diffuser. Lastly, there's the coffee cup. This is essentially when your coffee is ready for consumption. Just like the diffuser, when you push the cup to dispense the water, it acts like a free jet, and by the Torricelli relation, the water will issue at a velocity that is related to the pressure.
In conclusion, a coffee machine is an incredibly simple machine. All it does is take a reservoir of water, heat it, and then run it through coffee grounds. And through that process, you get a nice warm cup of coffee in the morning.